This video is brought to you by mywayteaching.com.
How can you charge a metal sphere positively without touching it? This is the question. See, in this figure A, it shows an uncharged metallic sphere on an insulating metal stand. So in order to charge this sphere without touching it, we should follow some procedure. First, you just bring a negatively charged rod close to the metallic sphere. As you can see in this figure B, as you can see in this figure B, isn't it? You just bring negatively charged rod close to the metallic sphere. As the rod is brought close to this sphere, the free electrons in this sphere move away due to repulsion. Since this is negatively charged, all the electrons move to the right side of the sphere due to repulsion, and the near end becomes positively charged. Positive charges are filled to this side, isn't it? And this process of charge distribution stops when the net force on the free electrons inside the metal is 0. And you just connect the sphere to the ground by using a conducting wire, as you can see in this figure. And in that case, the electrons on the right side, the electrons which are there, all those electrons will flow to the ground. Whereas the positive charges at the near end, they'll remain held there due to the attractive force of the negative charges on the rod. Okay. Now you just disconnect the sphere from the ground. The positive charge continues to be held at the near end. Okay. Remove that electrified rod now. The positive charge will spread uniformly over the sphere, as you can see in this figure E. So in this experiment, the metal sphere gets charged by the process of induction and the rod does not lose any of its charge. And even we follow similar steps in charging a metal sphere negatively by induction. In that case, what we have to do, we should bring a positively charged rod near to it instead of bringing a negatively charged rod. So in that case, electrons will flow from ground to the sphere when the sphere is connected to the ground with the wire. Okay. Now let us study some basic properties of electric charge. So already we know that there are two types of charge: positive charges as well as negative charges, and their effects tend to cancel each other. So here we shall see some of the basic properties of charge. See, if the sizes of charged bodies are very small as compared to the distances between them, we treat them as point charges. Okay, if size is very small compared to the distance between them, we call them as point charges. All the charged content of the body is assumed to be concentrated at one single point in space. Okay. So now let us study the first property of the charges, that is additive additivity of charges. See, if the system contains 2-point charges, one say as Q1 and the other one say Q2, then the total charge of the system is obtained by simply adding algebraically Q1 and Q2. Total charge, if you consider this as one system, the total charge of this system is obtained by simply adding these two charges. That is, Q is equal to Q1 plus Q2. That is, charges add up like real numbers, or they are scalars like the mass of a body. In general, we can say if the system contains n charges like Q1, Q2, Q3 up to Qn, then the total charge of the system is given by Q1 plus Q2 plus Q3 up to Q1. Okay. Charge has magnitude but no direction. So it is a scalar quantity which is similar to mass. But there is one difference between mass and charge. See, mass of the body is always positive. Isn't it? Whereas charge, it can be positive, it can be negative also. So proper signs have to be used while adding the charges in a system. Okay. For example, you just consider the total charge of a system containing 5 charges plus 1 plus 2 minus 3 plus 4 minus 5. So if you want to calculate the total charge of the system, you just add these with proper signs. Then we get minus 1. So signs are very important in adding the charges. So this is the first property of charges. Now let us see the second property. Charge is conserved. So we already hinted to the fact that when bodies are charged by rubbing, there is transfer of electrons from one body to the other, isn't it? And no new charges are either created or destroyed. So a picture of particles of electric charge enables us to understand the idea of conservation of charge. See, whenever we rub two bodies, what one body gains in charge, the other body loses, isn't it? It's not like some extra charges are added or it's losing some charges. No, it is not like that. It's just the transfer of charges from one body to the another. If one body is losing the charge, obviously the other body is getting the charge. So, within an isolated system consisting of many charged bodies, due to interactions among the bodies, charges may get redistributed, but it is found that the total charge of the isolated system is always conserved. Okay? The total charge of the system is always conserved. Conservation of charge, even it has been established experimentally. It is not possible to create or destroy net charge carried by an isolated system, although the charge carrying particles may be created or destroyed in a process, but not the charge. Sometimes nature creates charged particles. A neutron turns into a proton and electron. The proton and electron thus created have equal and opposite charges, and the total charge is zero before and after the creation. Okay, even though neutron, we know neutron is electrically neutral. So whenever neutron it gets converted into proton and electron, this proton and electron, they have opposite charges. Proton will be having positive charge, electron will be having negative charges. So again the net charge will be zero, isn't it? So that is neutral. So there is no creation or destruction of charge here. So the total charge of an isolated system is always conserved. Okay. Let us see the third property of charge, quantization of charge. What is this quantization of charge? See, experimentally it is established that all free charges are integral multiples of a basic unit of charge, which is denoted by E. The charge Q on a body is always given by Q is equal to NE. Okay, where N is any integer, it can be positive or negative. This basic unit of charge is the charge that an electron or proton carries, E, charge of an electron or proton. By convention, the charge on an electron is taken to be negative. Therefore, charge on an electron, we will write it as minus E, and charge on proton is taken as positive. So, we will write it as plus E. Okay. The fact that electric charge is always an integral multiple of E is termed as quantization of charge. So we can express the electric charge as an integral multiple of E. So we call this as a quantization of charge. See, there are large number of situations even in physics where certain physical quantities are quantized. This quantization of charges, it was first suggested by the experimental laws of electrolysis, which is discovered by Faraday, and then it was demonstrated by Millikan in 1912. So in international system of units, the SI unit of charge is given by Coulomb. This is the SI unit of charge. Okay. And it is denoted by the symbol C. A coulomb is defined in terms the unit of the electric current which you are going to learn. So we can define coulomb mathematically, that is 1 coulomb is nothing but 1 coulomb is the charge flowing through a wire in 1 second if the current is 1 ampere. So it is nothing but the charge flowing through the wire in 1 second if the current is 1 ampere. So this is the definition of charge. This is the definition of 1 coulomb. And the value of this E is given by 1.6 into 10 raised to minus 19 coulomb. So there are about 6 into 10 raised to 18 electrons in a charge of 1 coulomb. Okay. In electrostatics, charges of this large magnitude are seldom encountered, and hence we use even smaller units like 1 microcoulomb, that is nothing but 10 raised to minus 6 coulomb, or we'll even use 1 millicoulomb, that is 10 raised to minus 3 coulomb. Okay. If the protons and electrons are the only basic charges in the universe, all the observable charges have to be integral multiples of E. So thus, if a body contains N1 electrons and N2 protons, then the total number of charge on the body, we can write it as N1 into E plus N1 in N2 into E, N1 into minus C, since N1 and N2 are integers. Okay, we can write it as N2 minus N1 into E. Their difference is also integer. Thus, the charge on any body is always an integral multiple of E, and it can be increased or decreased in steps of E only, because the step size is E. The charge of a body can decrease or increase in units of E, it is not visible. The grainy nature of the charge is lost and it appears to be continuous. We can compare this with the geometrical concepts of lines and points. That is, a dotted line viewed from a distance, it appears continuous to us, isn't it? But it is not continuous in reality. Because many points are close to each other, normally it gives an impression of a continuous line. So when we take many small charges together, it appears as a continuous charge distribution, but that's not true in reality. At the macroscopic level, one deals with charges that are enormous compared to the magnitude of charge E. Say 1 microcoulomb contains something like 10 raised to 13 times the electronic charge. So the charge can increase or decrease only in units of E is not very different from saying that charge can take continuous value. The quantization of charge, it has no practical consequence and even it can be ignored. At the microscopic level, where the charges involved are of the order of few tens or hundreds of E. They can be counted, they appear in discrete lumps, and quantization of charge cannot be ignored at that microscopic level. Okay.